Okay, guys, so this is a lecture about some of the non-ideal characteristics of transistors. This is generally an important topic, but and that's like very broad and like critical to chip design, especially in modern processes or tighter processes. But it's especially important if you're picking something like the paper about the um, alpha model of the transistor. So I'm gonna record this separately because you may or may not be going using looking at that paper, but um, this is an important topic by itself. So there's the ideal behavior of a transistor. So let's just look of a MOSFET. So this is so-called, this is like so-called a Shockley long channel transistor model that was good for many years. And basically it comes down to this characteristic of if I draw the drain source versus the drain source voltage versus the drain source current. What you'll see is if the gate source voltage of the transistor, so this is gate, drain, source. So if the gate source voltage of the transistor is less than the threshold voltage, then the device is off. So as long as that's going on, typical threshold voltages are, so typical V sub T might be 200 millivolts to 500 millivolts. Depends on the process and the type of transistor, etc. But as long as that's the case, basically you're going to get the transistors off. There is no current. So all the curves, no matter what VDS does, it doesn't matter. You're going to be lying around, IDS is going to be zero, regardless of what happens. Then you get this region, so-called linear region. So once you get past, the gate source voltage ends up being, so here you'd have to be, not only does VDS, so this is for these cases, these two cases, VGS has to be greater than VT. And for those cases, the transistor turns on. And when the transistor turns on, depending on the value of V gate source, depending on VT, you'll have a series of curves that are going to look like this. So this is, say, VGS 1, VGS 2, VGS 3, and basically, VGS 1 is greater than VGS 2, greater than VGS 3. So when the gate source voltages go up, you basically get a linear type performance, so-called, here. So this is before VD goes to some voltage VD sat. That VD sat is defined as VGS minus VT. So, so for each one of these curves, it means that this value of VD sat is going to be different and drifts forward. So this will be, let's call this VD sat 1 corresponding to VGS 1, then you're going to get like VD sat 2 corresponding to VGS 2, and VD sat 3 corresponding to VGS 3. So for each one of those places, basically you get the linear point goes a little bit further for a higher VGS. And anything below here, you get this kind of equation where it's both a function of VGS, VT, but it's also a function of VDS in this regions. Okay. And then you get into this regions here past VD sat where you're square law dependent on VGS only. So there's no dependent on VDS, and these things go flat with VDS. Okay, and then beta is the mobility. In this case, that's the mobility of an NMOS, so mobility of electrons, the oxide capacitance, the width over the length of the device. Okay, so that's the ideal Shockley model, or the level one model. Probably the model you guys are most familiar with is what you learned. But what happens when you make sort of shorter channel devices, you end up having some major differences between that curve and what you actually get. And this is an example of a 65 nanometer process, which is a supply voltage of 1 volt, and it's showing the current, the drain current versus the drain voltage. So you immediately see some differences. So one of them is that when you get into the saturation curve isn't flat. So this is an ideal flat gray case. The black is the ideal, and the blue is the non-ideal. And you can see it doesn't really go flat. It has a slope, so it's dependent on VDS. The other thing that you can see is that you get much less saturation current than you were expecting according to the model. So for example, or according to the ideal model. So the ideal model, for example, the VGS of 1 volt uh, says you're getting something like 1.2 milliamp, but in the blue you say it has the VGS of 1 volt and it's only giving you 800 microamps, something like that. So almost 50% less current. So you see a bunch of differences between in the smaller models, in the smaller processes between the ideal model, the Shockley model, and what you get. And this is caused by a few different things. So we're going to talk about those in detail. And I want to really focus during this lecture on the on current of the device. There's really non-idealities both in the on current and the off current of the device, but I'm going to leave the off current for now because at least that paper, the alpha model, is really focused on the on current. Okay, so basically the reason the on current has these issues is really caused by the high electric fields in and around the channel. So, one of the things is, well, let's see, do I have the oxide thickness somewhere here? I don't see it. But anyway, so one of the things that immediately comes to mind is, why is there electric fields? Why are those really high in short channel devices? Because, we've only, let's say the supply voltage here in the case of this IBM process is only 1 volt. We're not talking about 1,000 volts or something. But you got to remember that this this VDD voltage of 1 volt is dropping across a very thin, very short distances. So the electric field is voltage. Oops, is the electric potential, so voltage over whatever distance that voltage is dropping across. And you got to remember that the oxide thicknesses in these devices might be, I don't know what they might be, but let's say maybe they're like 100 angstroms or something like that, on the order of that. Maybe they're only 30 angstroms, maybe 50, maybe 100, maybe 150, but that's 100 times 10 to the minus 10 meters. So very, very small distance, and the space between the drain and the source is also the length of the transistor. And we're saying that 65 nanometers, or 65 times 10 to the minus 9 meter. Again, a very, very small number. So you plug in these really, really small numbers in the denominator here, and you get an enormous electric field in these MOSFETs, in these short channel devices. So there's two kinds of different high electric fields that happen in the channel and cause problems. One of them is the vertical electric field, and the other one's the lateral electric field. So if I draw the MOS transistor, so you'd have a source, a drain, and a gate. So this is the gate, this is the source, this is the drain. So the vertical electric field is dependent on the gate source voltage. So basically, it's the gate to the source voltage or gate to channel voltage. And the reason why this causes a problem is because in this case, for example, the channel is going to be, once this device starts working, the channel is going to be made out of electrons that are shooting across here. And what happens is a gate source voltage that's very high in value attracts, it's positive in value. And so it's attracting these negative electrons to the gate and to the surface of the silicon. And what happens is the surface of the silicon is just is any kind of a surface, has non-uniformities, has very, very, very tiny at like the atomic level non-uniformities. And that tends to slow down the electrons. Okay, so that's the first thing. So the vertical electric field refers to the electric field this way. Okay, actually it's yeah, it's going from positive to negative, I guess. So I guess it'd be going like this, electric field, and pulling the electrons that way. So that's the vertical electric field. And then the lateral electric field is the electric field from the drain to source that, and we'll see why that has a tendency to reduce the mobility of the electrons once it gets too high, or the mobility, yeah, and so the velocity doesn't get as good as you would expect. Okay, so in either case, basically you end up in a situation where, let's see, this didn't come out here, this equation, but the basically there's a the mobility of a, let me just draw you guys what we mean by mobility in case you don't remember it. So mobility, when you have an electric field in silicon, and let's say you have the velocity of an electron, or it could be the velocity of a hole, whichever. If it's an NMOS, you worry about the velocity of an electron. If you have a PMOS, you worry about the velocity of a hole in the channel. And what happens is, as the electric field goes up, so does the velocity of the electrons or the holes. They have um, um, different slopes. So the electron mobility is usually higher than the hole mobility by a factor of two or so. So this would be for a hole, and this would be for an electron. And so the slope here, whoops, the slope here is the mobility. So mobility of an electron, and the slope is the mobility of a hole. Okay, so you would expect that as you electric field goes up, the velocity would just keep going up. But what happens actually is the electric field goes up. This is vertical. So again, this is from the gate to the channel, the mobility degradation there. Basically, you end up in a situation where you end up with an effective. So this equation for this behavior is mu is mo so sorry, it would be that velocity is mobility times the electric field. So mobility would be velocity over the electric field. But what happens is you end up with kind of an effective, instead of this, you end up with an effective mobility, which is more like 540 centimeters squared per volt second. over 1 plus VGS plus VT over 0.54 volts over emitter T oxide to 1.85. And there's a corresponding reduction in mobility for the holes because of this high electric field. And so, again, the plot didn't come out here, but basically what happens is, apologize about that, guys, but anyway, what end up with is you end up with this plot instead of looking like this. So for a vertical electric field, you end up at some electric field, this thing starts saturating. So it like no longer increases with increasing electric field. And that happens a little bit later in the holes. So this is called the critical field for the electrons, and this is called the critical field for the holes. And so when you look at the velocity saturated IV curve, you end up with something different than the ideal. So for example, specifically in the saturation current, you expect in the ideal transistor model or the Shockley model to be your saturation current to be square law dependent on VGS minus VT. But in reality, what happens is that in the short channel effect, what happens is you end up being sort of linearly dependent on VGS minus VT, and you multiply that by some maximum velocity. So Vmax is max velocity of carriers. And so that brings us to how, so basically you end up with, a pretty complicated equation as it turns out, because you can see how the velocity numbers are now they're dependent on, sorry, the mobility is dependent on the gate source voltage. You end up with, anyway, kind of a messy equation. So to do a hand calculation, people have come up with different models of how to do hand calculation. And one of those is the alpha power model, which is what the alpha model power paper is describing, it's proposing as a simple model for doing hand calculations when you have this complicated velocity saturated situation.